So as you might expect, based on this first problem, the first thing that we're taking a look at here, we are going to be working with sine, cosine, and tangent today. And the first thing we've got to do with that is we've got to check that we're in degree mode. So to make sure that your calculator is in degree mode, I've given you a way to test it here. So in your calculator, let's do sine of 30 degrees. If you're on a graphing calculator, you pretty much type it in as you see it. You would type sine first, and then you would type in 30 and press enter. If you're on a scientific calculator, you actually press 30, and then you press the sine button after that. Now, if you do that, and it gives you an answer of 0.5, your calculator is set up in degree mode. It's good to go. However, if it's not, well, then you need to make sure that your calculator is in degree mode. On the graphing calculators, like the TI-83, TI-84, press the mode button. That's at the very top, right next to the second button. If you press mode, you then can arrow down and select degrees and press enter on degrees on the graphing calculator. And then redo the calculation, make sure that sine of 30 gives you 0.5. Now, if you're on a scientific calculator, like one of mine that you might have borrowed during class, on one of these, you'll know you're in degree mode because it should say DEG at the very top of the screen. DEG is short for degrees. But if it's not, each of these calculators looks a little bit different in how it's going to look. On this particular one that I have that you can borrow during class, it's the DRG button, which is right next to the second button at the very top there. As you press that button, you'll notice it cycles through degrees, and as well as a couple other options there. So make sure you are in degrees, and make sure that you are able to do sine of 30 and have your calculator give you 0.5. Now, there are multiple ways to measure degrees, or measure angles. Degrees is the most common one that we've used so far, but radians ends up being really useful, especially in a lot of scientific applications and things like that. So that's why we always have to choose this at the start. In fact, a lot of calculators are even going to default to radians. So you always want to check this first thing every class. Make sure that you are in degree mode. All right, we're going to be using these to calculate each of these values. So on your calculator, please do sine of 60 degrees. And then round your answer to 4 decimal places. Now, when you do that calculation, you should be getting an answer here on your calculator that looks like this. Now, of course, it's a big, long decimal. It's a decimal that goes on forever and ever and ever, right? Well, we don't want to give the whole thing. Remember, we're just going to round this to 4 decimal places. So, quick reminder when doing our rounding, we look at that 4th decimal place, and then we just look at the one next number after it. I don't care about anything after that one next number. So I just look at the 2. It's a 2. So that means that it's going to leave the 0 as a 0. The only option is that it either stays a 0 or it goes up to a 1. And because it's a 2, it stays a 0. So there's your answer for sine of 60. It is 0.8660. The next problem, we're going to be doing cosine of 45 degrees, but you'll notice I wrote it differently this time. In the first one, sine of 60, there's no parentheses there. All right, so the first one had sine of 60 without parentheses. This one has the parentheses in it. What do the parentheses do? Nothing in particular, actually. The parentheses do not change what it means, what it equals, or anything like that. So for this one, you're going to do the same thing. Just do cosine of 45. So when you do that calculation, this is the big long decimal that your calculator gives you. Again, we're rounding it to the 4th decimal place, which is where that 1 is. Since the next digit is a 0, it stays a 1. So cosine of 45 is 0.7071. Finally, calculate the tangent of 85, please. Tan 85. All right, so for this one, when you do that calculation, this is the number that it should be showing you on your calculator. Now, again, we're looking to round to the 4th decimal place, so that's where the 0 is. Is it going to stay a 0, or is it going to round up to be a 1 here?
1.
It is going to round up to be a 1, yes, because the next digit after that, which is the only one I care about, is a 5. And remember, if it is 5 or more, it rounds up. So your answer here is 11.4301. Then, shifting gears a little bit, we're going to take a look at another type of function that comes up with these same sorts of things. All right, so we're going to be calculating here this sine. It looks like sine to the power of -1. But that's not actually how we want to read this. We actually read that as inverse sine of 0.4. It has to do with this concept of inverse functions, which comes up a lot in Algebra 2. But you write something as to the power of -1, and what you're actually doing is saying it's the inverse operation, the inverse function of that. So we're going to be doing inverse sine of 0.4. Now to get to inverse sine, usually on almost every calculator you'll notice it written above sine. So it is almost always second sine. So you're going to calculate this the same way that you did before with this regular sine, except you're going to have to press second before you press sine. When you do that calculation, if you do it correctly, this is what you should be looking at. So make sure you can get that number out. On a graphing calculator, you would type in second sine 0.4 equals. On a scientific calculator, 0.4 second sine. All right, so this is what we get as our answer, and again we round it, right? What are we rounding it to in this problem? Notice this one's 2 decimal places. Each time you hit a new problem, check to see what it says to round to. This one changed. So in this case, we're going to 2 decimal places. That's where the 7 is. The only question is it going to stay a 7 or is it going to become an 8? It does become an 8. And so our answer here is 23.58. All right, now the first one, it had the parentheses in it. The second one doesn't. What does that change? Nothing. It does mean the same thing. So why am I writing it both ways? Because I need you to see and get used to the fact that it does mean the same thing. Because depending on whose work you're looking at or who wrote the textbook you're working from or whatever, you'll see it both ways. And so I just need you knowing that it's the same, because I don't want them writing it slightly differently and all of a sudden you're thinking it doesn't mean the same thing. All right, next up, we're doing cosine of 0.75, or inverse cosine rather of 0.75. You notice our big long decimal here? We're rounding to the second decimal place. Since this is a 9, yes, we do round it up. So it's going to be 41.41. And then for the last one, we're doing inverse tangent of 0.89. That gives us 41.669. And again, I look at that one next decimal to see, does it stay a 6 or does it become a 7? Yes, it does become a 7. And so it's 41.67 for our final answer there. Now, if you're able to get all of those answers, that means you got the basic calculations down when it comes to sine, cosine, and tangent. Now, if you know how to do those calculations, then you're also going to be able to solve equations that I give you with these as well. So that's where we're going to go next. We're going to solve this equation. So please write down the equation and then the work as we go and do it together here. So in this case, we're solving for x, right? Now notice where x is. X is trapped inside of cosine, which is all cos means, just short for cosine. So if x is trapped inside of cosine, I need a way to undo cosine. Well, in order to undo cosine, I need to use the inverse cosine operation. So we're actually going to be doing the inverse cosine of both sides of this equation. That's that cosine to the power of -1. Remember, that means inverse cosine. Inverse cosine undoes cosine. And so if I do inverse cosine of both sides, what it does is it cancels out the cosine on the left side, just leaving me with the x. And of course on the right side, I have to actually do the inverse cosine of the 0.25. So notice how we showed this in the algebra. By doing inverse cosine of both sides, I just get the x on the left, And on the right, I'm writing the inverse cosine of 0.25. Now, some of you might be tempted to say, oh, okay, then I can go straight to the decimal. So you plug it in your calculator, you get your answer. Please show this step of work before you do that. By showing that step of work, we're not only showing anybody who looks at this later how we did it and showing that we did do it, but we're showing ourselves. So like if we're doing this on a quiz or something like that, you can look back and you can see in your work how you did it. And the act of writing it out also creates a reinforcement in your own brain that helps you to remember the process that we just did to get this answer. Now, one other little detail-y thing to notice here. You notice I wrote in my answer here a degree symbol. Anytime you do inverse cosine, it's going to give you an angle as an answer. Regular cosine takes an angle and gives you a number. Inverse cosine takes a number and gives you an angle. Same thing works with sine and cosine and tangent as well. All of them work the same kind of a way. Just kind of an aside to see how those things work. Now, having done that one, we can also see problems where we start with the inverse cosine in there and we need to solve the equation. So write down this equation, and again, we'll solve it through together. All right, so in order to do this one, we start with inverse cosine. So I need some way to undo inverse cosine. Well, when I started with cosine, I undid it with the inverse. It works both ways. If I want to undo the inverse cosine, I'm going to take cosine of both sides of the equation. So we're going to be doing cosine of both sides of this. And the beauty of doing cosine is cosine undoes inverse cosine. So it's canceling that inverse cosine out on the left-hand side. It's just like multiplication undoes division and division undoes multiplication. It's the exact same idea. It's just more complicated looking. So when we do that, of course, on the left side we just get x. On the right side, we're going to get the cosine of 20 degrees. Now, of course, this is just like what we did earlier with our calculators, right? Where we're going to do cosine of 20 degrees. Now, notice it's regular cosine this time. So no second cosine, just cosine. When you do that, you should be getting an answer here of about 0.94. Now then, a little bit of detailing behind the scenes stuff. We're going to be getting more into using this sort of thing tomorrow. Today's main focus is the stuff that we just went through. But I do want us to be able to touch on this because we're using sine, cosine, and tangent today, but we haven't really talked about what they're all about. So I do want to talk about what these really mean. Now, sin, no, we don't read it as sin. Yeah, I know. It'd be so much more fun, right? But it's actually sine. Cos is short for cosine. Tan is short for tangent. So these just represent the actual ways we write the function for sine, cosine, and tangent. If we write out sine the long way, we pronounce it sine, not sin, because it actually has an E on the end. For the same reason I don't say cos, I say cosine when I see that, because that's just what it's short for. And of course, tan is short for tangent. Now, each of these represents a different kind of a ratio of sides in a right triangle, and specifically right triangles. So we're going to be using a lot of right triangles. Now, at the very end of geometry, you will have seen sine, cosine, and tangent come up a decent amount. And some of you got a pretty good hang of it then, and some of you didn't. And part of it depended upon how much time there was left for that unit at the end of geometry. So we're going to do a little bit of review on that stuff here to make sure that you can kind of see how it's all going to work. So let's take a moment, add this into your notes, please. And then we're going to see how we can make use of this and what it really means in the big picture. All right, now, as you take a look at this, notice all of these are starting from a right triangle, and so that's the drawing we have over here. The square in the corner, remember, means that is right. And so each of these represents a different combination of the three side lengths of a right triangle, which, remember, we've recently been practicing are called opposite, adjacent, and hypotenuse. And so it's just different ways of taking that same information about the side lengths and then relating it to an angle. You notice in our picture here that this particular angle is marked. That's because this angle is the one from which this side is the opposite and from which this side is the adjacent. If I changed which angle this was going from, it would change which one was the opposite and the adjacent. Keep that in mind as you use this as a reference. But the hypotenuse, notice it doesn't change. The hypotenuse will always be opposite the right angle. Also, another way to remember hypotenuse is it's always the longest side. Now, I want to look at one particular example of this. So I'm going to focus in on cosine here for an example. And the cosine of 60 degrees equals exactly 0.5. If you plug that in your calculator, it tells you 0.5. But what does that really mean in terms of these triangles that we're talking about? Well, here's a triangle. Remember, cosine is adjacent over hypotenuse. So like if I take this particular triangle here, the adjacent is the 1. So that means this would equal 1 over the hypotenuse, which in this example is 2. Notice cosine equals 1 over 2. What does 1 over 2 equal? 0.5, right? But of course, that was just one example with that triangle. What if I stretch that triangle out? This angle is still the exact same angle. It is still 60 degrees. Notice our sides doubled. If I take the adjacent, notice my adjacent here is 2. My hypotenuse here is 4. What is 2 divided by 4? 1/2. What if I enlarge that triangle even more? Adjacent over hypotenuse. 3 over 6. It equals 0.5 still. Notice that no matter how I change that triangle, if I keep this angle the same, the ratio between the side lengths also stays the same. That's why these values exist, and how we can know that cosine of 60 always equals the same value, because it will always equal whatever the adjacent over the hypotenuse is, and in this case always 0.5. So having seen that, we now can kind of see what sine, cosine, and tangent actually mean. But again, I'm going to expect you to be remembering these in the near future as well. We're going to need to have these actually memorized. And some of you are the sorts where you're going to look at this and you're just going to memorize sine equals opposite over hypotenuse. And you're good with memorizing, and that's fine if you do. But usually we need a way to check ourselves, or a way to remember. And so there is a single word that you probably learned back in geometry to remember all of those. Yep, SOHCAHTOA. If you can remember how to spell this, then you're going to remember sine, cosine, and tangent. Let's take a look at why this helps. The S up here, that stands for sine. Remember our definition of sine. Sine equals the opposite over hypotenuse. SOH tells me that sine is opposite over hypotenuse. C, what do you suppose the C stands for? It's cosine. And notice what follows cosine. AH. Cosine is adjacent over hypotenuse. And of course the T, tangent, that's got to be OA, opposite over adjacent. So SOHCAHTOA is a great way to remember the definitions of sine, cosine, and tangent. And you'll often hear me describe it that way. I'll say, what's the definition of sine? The definition of sine is this, the opposite over the hypotenuse. That's what I'm talking about when I say that. So this is a nice way to memorize these definitions. This is also worth putting into your notes so that you have it there to help yourself remember how to remember all these values.